first price auction. As an example of Bayesian analysis, we study the standard first price auction in a simple setting. A single item is auctioned between two players, Alice and Bob. Each has a private value for the item. A is Alice's value and B is Bob's value. While we already saw that a second price auction will allocate the item to the one with higher value, here we ask what would happen if the auction rules are the usual first price ones. The highest bidder pays his bid. Certainly Alice will not beat A, since if she does, even if she wins, her utility will be 0. She will thus need to beat some x which is less than A, but how much lower? If she knew that Bob would beat y, she would certainly beat x equals to y plus epsilon, as long as x which is less than equals to A. But she does not know y or even b, which y would depend on. She only knows the distribution dBob over b. Let us now see how this situation falls in the Bayesian-Nash setting described above. The type space T Alice of Alice and T Bob of Bob is the non-negative real numbers, with T Alice denoted by A and T Bob denoted by B. The distributions over the type space are D Alice and D Bob. The action spaces X Alice and X Bob are also the non-negative real numbers, with X Alice denoted by X and X Bob denoted by Y. The possible outcomes are the set of Alice wins, Bob wins, with V Alice of Bob wins equals to 0, and V Alice of Alice wins equals to A, and similarly for Bob. The outcome function is that Alice wins if X is greater than or equals to Y, and Bob wins otherwise. We arbitrarily assume here that ties are broken in favor of Alice. Finally, the payment functions are P Alice equals to 0 whenever Bob wins, and P Alice equals to X whenever Alice wins, while P Bob equals to Y whenever Bob wins, and P Bob equals to 0 whenever Alice wins. Our question translates into finding a Bayesian-Nash equilibrium of this game. Specifically, we wish to find a strategy S Alice for Alice given by a function x of A and a strategy S Bob for Bob given by the function y of B that are in a Bayesian equilibrium, i.e. are best replies to each other. In general, finding Bayesian-Nash equilibria is not an easy thing. Even for this very simple first price auction, the answer is not clear for general distributions D Alice and D Bob. However, for the symmetric case where D Alice equals to D Bob, the situation is simpler, and a closed form expression for the equilibrium strategies may be found. We will prove it for the special case of uniform distributions on the interval between the 0 and 1, the closed interval between 0 and 1. Similar arguments work for arbitrary non-atomic distributions over the valuations as well as for any number of bidders. Lemma 9.45. In the first price auction among two players with private distributions of the private values A, B, uniform over the interval, the closed interval between 0 and 1, the strategies x of A equals to A over 2 and y of B equals to B over 2 are in a Bayesian-Nash equilibrium. Note that in particular, x is less than y if and only if A is less than B. Thus, the winner is also the player with highest private value. This means that the first price auction also maximizes social welfare, just like a second price auction. Proof. Let us consider which bid x is Alice's optimal response to Bob's strategy y equals to B over 2 when Alice has value A. The utility for Alice is 0 if she loses and A minus x if she wins, and pays x. Thus, her expected utility from bid x is given by ULS equals to the probability of LS wins with bid x times A minus x, where the probability is over the prior distribution over B. Now, LS wins if x is greater than or equals to y, and given Bob's strategy y equals to b over 2, this is exactly when x is greater than or equals to b over 2. Since b is distributed uniformly in the closed interval between 0 and 1, we can readily calculate this probability. 2x for 0 less than or equals to x less than or equals to 1/2, 1 for x which is greater than or equals to 1/2, and 0 for x which is less than or equals to 0. It is easy to verify that the optimal value of x is indeed in the range 0 less than or equals to x less than or equals to 1/2, since x equals to 1/2 is clearly better than any x greater than 1/2, and since any x less than 0 will give utility 0. Thus, to optimize the value of x, we need to find the maximum of the function 2x times a minus x over the range 0 less than or equals to x less than or equals to 1/2. The maximum may be found by taking the derivative with respect to x and equating it to 0, which gives 2a minus 4x equals to 0, whose solution is x equals to a over 2 as required.